The zener is 5-volt zener. It's 5-volt, the current flows from the cathode to the anode, and if it's behaving as a diode, current flows from the anode to the cathode is 0.7. So set up Kirchhoff's current law, solve for V out, and find it and justify your assumption. So from the circuit configuration, we decide how does current get from 10 volts to ground, right there. And logic, it has to flow downward through here. It flows down through this resistor, and it must flow out of that resistor. So there's three.
Hello everyone, I hope you're well. So I just want to make an announcement that after this class at 4 p.m. I'm going to hold an office hours online Zoom. Everybody is welcome to join. It's going to be about midterm as well. If you have any questions about midterm, you can ask me. It's going to be a similar theme as this one. If you pay attention to this class, it's also a review of midterm. So you probably not going to need it. But just in case if you have any question, you'll be welcome to join and ask anything you like. Alright? So I'll send the Zoom link hopefully in an hour. Alright? Yeah.
Can you record it, please?
Record. Yeah, but to be honest, you're not gonna get any benefit from the recording. Yeah. It's just better that you join the class and listen to me. And if you have questions, unless you are not satisfied, I'll be there. Alright? So no matter how much time it takes.
Yeah, but if you can't make the time, wouldn't it be better to have it recorded? And then if we had, to just relook this. Just
So
to have
it's
that.
going to be more of a question answer. Obviously, I will be trying to do one, the previous midterm exam, which is uploaded, right? Few questions from them as well, just to give you an idea. However, it's more of a question answer based thing. But I guess I can record it for you, but I don't feel there's going to be any benefit to that because it's going to be question from students. If you, from my experience, students who not gonna take the tutorial at least 2 days before the class, they're not gonna take the recording as well. So it's just better to be there. But just in case you have any other questions, maybe tomorrow, just reach out to me and maybe I can hold office hours for you as well. I understand you have your midterm exam on Friday, so even if somebody is not able to join my tutorial, right, just drop me an email and ask me about it. And if we are able to, maybe we can hop on a Zoom call as well. So that, alright? You good? You good? Don't worry, if you have any questions, just let me know, I'll hold up.
Wait, well, no, but that's what I'm saying. If I don't know what the right questions are to ask, that's why I'm
It's
saying
alright.
it would be good to have the recording.
It's alright, no worries. Just come on a Zoom call or maybe email me and we will go through the solution. That's it. Don't worry about it. I know you guys must be a bit scared about the exam, but you're not. That's good. But it's alright.
What are your hours going to be on Friday after the exam?
After the exam, you want an office hours after the exam?
Yeah.
After the
Friday
exam,
or Monday.
oh yeah, we can do Monday. Yeah. Most probably not on Friday, but we can do it Monday. Definitely. Yeah. Just drop me an email before and to let me know what the topic of discussion is, what do you want to discuss, and that way I'll be better equipped to answer your questions. Sounds good? Just don't worry about it. If you have any questions, drop me an email. That's it. Alright? Sounds good? Alright guys. See you. Have a nice day.
All right, so this is one form of a problem to expect is a zener and one or more regular diodes in the same circuit. This particular problem, this is set up KCL, solve for the V out voltage, and then justify your assumption. So we try to easy guess first. The zener is a 5-volt zener. If current is flowing through D1 zener, what's the voltage here?
The voltage there is, the voltage at VO would be the voltage, so it'd be 10 minus the voltage drop of the resistor minus the voltage drop of the resistor.
Now this, all right, now this problem is, because the zener is after the 1K resistor, it means that V out is an unknown, and we have to solve for VO here. So this problem does not give an obvious result by the V out, so we need to write the KCL equation. That's what the problem says. Assume they're all on and write the KCL equation. So for resistor R2, this 1K resistor, the current through it is VO over R2. And that's VO over 1K. Resistor R3, which is over here, this current is V out minus 1 diode drop. There. So that's the voltage at this point. It's V out minus 1 diode drop divided by 1K. And then the current through resistor R1, we need to get the voltage at this point here. So the voltage at that point is V out plus the zener diode voltage. And that's because if this zener is on, this voltage here gets raised up by 5 volts in here. But it's still, it leaves 3 equations with VO unknown in the equation. And now it's a matter of solving the equations for VO. And that's the map that's shown here. Set up KCL and now solve for VO. It's a good idea to practice this problem. So this will kind of give an idea. The first problem, this version was fairly straightforward, except the voltage at this point is V1 minus 1 diode drop from the zener. And this version of it, this portion here, means you really got to solve the KCL equation. So spend time studying this problem. And again, that's another hint. I'm not saying you'll have this exact same problem, but it's something configured such that the output voltage that you're getting is going to have to be extracted from the KCL equation. That way you basically be in the mode where you recognize that it's not going to be obvious based on the circuit configuration what actually is happening with the diode. Now you're up there. Now this, one way to look at op amps and diodes, diodes are small. You have one bucket with all the diodes in it. Zener and diodes or germanium. But op-amps are lots of different buckets of circuits. So the op-amps are definitely a much larger field in order to review compared to the diodes and the Zener diodes. So again, we can open this up and start reviewing some op-amp problems. Some of these problems are not really suited for the time period that we have. You can start, this first problem is fairly straightforward. It's an op-amp circuit, and we recognize that it's an inverting op-amp, and it gives the batteries a plus or minus 10 volts, assuming the maximum current can deliver to the load. That's the op-amp limitation. It's 20 milliamp. It signals something about subsignals, but it says sketch the output voltage here in the circuit. And it says so what's the gain of this circuit?
Negative 100.
What is the gain of the circuit? The gain is negative 100, and the input is a voltage of 1 volt amplitude. So sketch the output. What does the output appear to be?
10.
So the prediction is that we apply 1 volt sine wave amplitude to this input with a gain of 100. The op-amp is going to clip at plus or minus 10 volts, and you're going to get square waves coming out. So
They already gave you the gain already in the circuit
what is that?
for the 100 gain.
The gain is 100K over 1K.
Okay.
Minus 100K over 1K. Now you're going to have that on your formula sheet, what your gains are. So it clips on the output. And a version like this is just, we just asked to identify the circuit. So what's the name of the first circuit here? What type of amplifier is it?
Inverting. Just,
Inverting op-amp?
yeah.
And what is the second?
Inverting.
And this is similar to your
Oh.
your partially symmetry homework problem. Basically, just cascade the gain. So this circuit has a gain of 7 times 5, which is 35. And here's another version using non-inverting op-amps. We just need to recognize how the feedback resistor is connected, and the non-inverting input goes into the pin 3 of the op-amp. So that's the same amplifier using non-inverting op-amps. Here's a low-pass filter circuit here. Assuming the input is 5 sine 2 pi 6000 T, the desired steady state output is 1.4 sine 2 pi 6000 T. Now right away we notice the input is 5 volts, the output is 1.4. That means that this is this circuit has to reduce the amplitude of the input. So R2 and R1 are not equal to each other because the input and output have different amplitude. Even with that, choosing R2 and R1 is straightforward. You just take the ratio of 1.4 divided by 5, and that's equal to 0.28. And arbitrarily, we can, there's hundreds of different combinations that will work. The gain, the desired frequency is 6,000, so the cutoff FCC make it much greater than 6,000. This says make it 60 kilohertz, 10 times 6,000. 60 kilohertz equal 1 over 2 pi R2 times C. Now, if let's say if we choose C is 0.01 microfarad, that's going to fix R2 value to 1.67K. And then in order to get this ratio of 1.45, R1 is solved to be 6K ohms. So we we've gone over two types of low-pass filters. One where the input and output are the same amplitude. In this version, the input and output are unequal amplitude. You just have to make a note of what's the leading number in these trigonometric forms that these are given. And notice it says also, what are the two DC supplies? So if a question says, choose your batteries, what would be good batteries for this circuit?
10 volts, 5 volts?
Any number above 8 volts less than 18 volts.
Okay.
So plus minus 12, plus minus 15, plus minus 8. All right, we'll skip this one. This is a op-amp limitation. This is where it's actually short-circuiting output of the op-amp. So we'll make a note. Whenever we say we're skipping something, make a note of that. Yeah.
In the previous problem, where you changed the gain by changing the resistor values, if in the same problem, would a answer be accepted if you changed the capacitor to make the cutoff frequency have a gain at that frequency to get that output signal? Would that be?
If it doesn't change the specification, it's fine.
Oh.
Yeah. So you only just be aware that if it 60 kilohertz is arbitrary.
Yes, of course. But I'm saying we would choose the resistor values to keep them the same, and then we would use the formula where it's 1 over the square root of 1 plus 1 plus the frequency that we want, which in this case would be 6,000 over the cutoff frequency squared, of course. And then we would have the gain be at 0.28, and then we would chain, and then we would just algebraically manipulate the formula until we get what we want the cutoff frequency to be for that.
You could do it, that's the way it's done in the homework.
Oh, okay.
In the homework assignment, you're designing it based on the gain at each frequency. This one is just saying the numbers are given. And op-amp limitations, there won't be any questions about op-amp limitations. Will there be a question about voltage level shifter?
No.
No question. You can go through this, but it's there, but there won't be questions about that. There can be questions about a comparator circuit. And comparators we identified because there's no obvious resistors on the schematic. So this question is saying sketch the out for 3 cases. And we'll just go over the first one. The amplitude of the input is 1 volt. And the batteries are plus or minus 12 volts. The 1 volt is applied to the non-inverting input. So when the input goes above 1 volt, when the input goes above, the reference is 0, so when the input goes above 0, the op-amp will switch positive. So starting at time 0, the op-amp switches to 12, and then it just keeps reverting back as the sine wave passes to 0. This last one, this is another hint right here. The second one, the third one says, replace the ground connection to pin 2 by a DC supply of roughly 5 volts. So the third version says, take pin 2 and connect it to 5 volts right here. So we're going to put 5 volts on here. What happens on the output of the comparator if we put 5 volts here? The source is still 1 volt amplitude.
It would never go on.
You can't switch because the 5 volts will win and it will always force the output to no output, to minus 12. So the output will be, that's how you draw a output. If the comparator doesn't switch, this is just saying it stays at minus 12. There will be a question about op-amps that won't, comparators that won't switch. So again, this is one we'll spend some time with. It's a simple problem. However, we have to understand how the comparator reacts to the input Anyone have any question about the integrator? Will there be a question, there won't be a question about the differential amplifier.
No different problem?
Not on this. Smith trigger, will there be a question about the Smith trigger?
No.
Question on the Smith trigger. Our inverting op amp, this is it gives the two resistors, the C factor is 33K, the R1 is 4.7K, the gain is minus R2 of R1, so it's minus 7.2. So it's saying to sketch the output, the input goes from 1 to minus 1, and the gain is minus 7.2. The output gets inverted, and it goes from minus 7.02 to 7.02. Now the question did say the batteries were plus or minus 10 volts. Is this op amp clipping?
No.
It's not clipping. Okay, so, and again, no question about op amp limitations. There's another one. This is a non-inverting midi amplifier square wave of amplitude 1 volt and 500 hertz by a factor of 2. So it's saying decide on the resistors. This is a non-inverting op amp. So to get a gain of 2, we take our equation V out over this VS is 1 plus R2 R1. So let's just make R1 equal to R2 and pick 1K. V out is 1 plus 1, 2. And we're done. That's fine. Another one, this is saying we want to have a gain of minus 12, and the batteries of 10 and minus 10 volts. And minus 12 identifies we need an inverter. The input is 50 millivolts. So that's irrelevant probably here. It's not asking if it's clipping. So we gain a minus 12, this R2 is 12K and R1 is 1K. Summer. Okay, there won't be a question about the summer. Again, there's a level shifter you don't expect. There's another low-pass filter, and that's actually the one we went over before. Here's a simple comparator. The op amp output should go high whenever the input signal becomes smaller than 4 volts. So this question was asking you to draw the circuit or design it. So the engineer here draws the op amp. We want the output to go high when the input becomes smaller than 4 volts. That means the 4 volts is the largest input to the non-inverting comparator. So whenever the input becomes smaller than 4 volts, the output will switch to the positive battery. So it's a pretty straightforward question. Just recognize that it's a non-inverting comparator. Another level shifter. Another Smith trigger. I think we went over this mystery circuit before. This is a voltage level shifter. There's some comparator design questions. I would go review through any questions about comparator. Definitely. Here's another low-pass filter. This low-pass filter, the way this question is set up, it gives 3 different signal generators on the input, and the filter is already designed, and it says find the cutoffs first. So that's pretty straightforward. The cutoff is 1/2 R2 times the capacitor, so it's 1.59 kilohertz. And then now it says do a simulation on paper. So this problem is similar to your homework assignment. It's saying calculate each of these 3 frequencies, what's the level on the output of the low-pass filter. So the desired is at .992, which is okay. The second frequency is .705, and then the third frequency is .032. So it's really filtering the third frequency here. And as I said, this one is similar to your homework assignment. There's a differential amplifier. That's another differential amplifier. Problems like this are really identifying the op-amp. The first one we haven't covered. This is a monostable circuit. This is an inverter. It's a summer, and then there's a low-pass filter. And the circuit, the same circuit. What is this circuit? Differential amplifier.